Okay. I got a cold, so I will be sneezing today. Sorry. If you are looking for the lecture slides, you can go to my lab webpage. The easiest way to find the link, of course, we have the teaching spreadsheet. My lab is basically NTUST, ME, no dot, NTUST, ME, Design Automation Lab. So if you look for these characters, the first one would be my lab webpage, and over the online lecturing, you can find the slides. I create those slides several years ago, so I'm using the same slides. You can, my TA this semester is not creating a new column. I think she will later on when she upload the teaching video. So she will also provide hyperlink for the PowerPoint. However, if you cannot wait, you can just go to the columns for previous semesters. They are the same slides. Now, back to today's lecture. We are going to, I think, solving the beam problem. Okay, so for a beam problem, this is a slide that we need to go through. Okay. So for an entire beam, and there could be any kinds of loads applied on top of it. And the loads everywhere can be different. So this is a general derivation. In a general derivation, there could be certain loads with different profile, but at this point, we're only talking about loads along y direction. So this is an analysis focusing on loads on y direction, and we're trying to figure out what would be the deflection along the y direction. So those so-called distributed loads, W, are applied on top of the particular element. And since we are making a small cut of the beam, this small slice is very narrow. So when you stand on top of this particular element, which is supposed to be super narrow, the load on top has the same value. Even though in reality the loads could be varying, but we are only focusing on one small area. So within this small area, we assume the loads are not changing. but W will be certain value at that particular point. So right at X, the value W equals to W of X. Then it depends on the problem or the reality. Then you figure out what is W. Okay. So now we are focusing on this tiny slice, tiny cut of the beam, and we have distributed loads on top. For the unit of the distributed load, W is having a unit of Newton over meter. Okay. So it's not Newton only. It's how much load is being applied within a certain linear area. Okay. Now, so later on, if we want to compute for the entire total force contributed by W, you need to multiply the width. Okay, so that's why we know the width right here is dx. In some of the derivations, there are W multiplying dx. That's basically calculating the total force contributed by the W. Okay? Now, basically, the first equation is the balance of force. We need to make some assumptions. Since we have some random loads applied to the beam, and we take a small slice of the beam. So on the left-hand side and the right-hand side, there could be moment and shearing forces. The only thing is we don't know how large they are. So in the this configuration, we assume, okay, on the left-hand side, there could be a shearing force V going up, and we have a moment going clockwise, M on the left-hand side. So on the opposite side of the material, there will be same amount of the shearing force and moment representing a pair of the shear force and the moment. However, if there's no external force, then there will be no change of shear and no change of moment. And since we have the external force, the force inside the material needs to balance out. So there could be change of the shear and change of the moment on either edge. So let's assume we treat the left-hand side as having the shear force V and shear moment M. And we say on the right-hand side we have shear force V and N as well, but there could be an increment of the shear and the moment, so dV and dN. The issue is it actually increasing or decreasing? So you need some math to figure out. Okay, but in current math symbols and certain definition of the symbols, we treat them as positive increment. If it turns out dV is negative, then that means the shear force on the right-hand side is smaller than the left. Okay? Now, based on that definition, we can now derive balance of force. So all the forces goes up equals to all the forces goes down. So here, W is a linear force, so you need to multiply the width. That's why W times dx. There's a shear force going up, V. On the right-hand side, you have shear force V and dV going down. So that's on the right-hand side. So all the forces going up equals to all the forces going down. That gives you a new relationship. It's called W equals to dV over dx. So if you would like to know how much increment of the shear force this material is carrying, then you need to figure out what's the value of W on the top. So if W is positive, then dV is positive. If W goes down, is negative, then dV is negative. Okay. So for balance of moment, basically you will study right at the center point. Okay, and the moment. Oh no, I think it's not on the center. It's on the. Yeah, it's on the center. So the equation on the left is the moment clockwise, and the one on the right hand side is the moment on counterclockwise. So the total moment clockwise equals to the total moment counterclockwise. So over here, B plus dV is the force right here, multiplying the distance half of the dx, and this is clockwise moment, right? And also V times half of the dx, also contributing a clockwise moment. And this guy is clockwise. M plus dm is counterclockwise, so it's on the right hand side of the equation. So by simplifying the equation you have right there, you end up with this new relation. So if you would like to figure out how much increment of the moment you will have, you need to know what's the shear force. So V equals to dm over dx. Okay? So if you later on, we need to do something here. So then we have the equation on the right. But now we know there are several things. You have W, you have V, and M. They are very related. And W, V has this relationship. V, M has this relationship. Okay? Now, deflection. So, why do we need to know about the deflection? So basically, due to the force, this particular element kind of deflects a little bit. So at the end, the beam could be having certain shape. So we would like to know the deflection along Y everywhere on this beam. It's important for mechanical design. Okay, so how do we compute for that? So we still focus on this particular element, and this time we are using the figure on the right. So there will be some new concept applied to this particular element. So first of all, this is an exaggerating drawing. So due to bending, this rectangular shape kind of being deformed into a pie shape. A pie. Taiwanese may not know. So this is like a pie shape. Okay? So kind of being deformed in such a way. Now, because over here, this is the neutral plane. So this arc length, there's no load on the neutral plane. So the length on the neutral plane remains the same. So this one remains dx. Okay? Now, since this is kind of being deformed into a pie, and there is an angle. So here is the angle of the shape. So d theta. Okay. But this is like you are coming into the element, focusing on the element, and take a good look of this tiny slice. Then you see small increment of theta. However, if you are stepping back and try to view this beam is being bended like this. Okay, so there will be a like a rotational center, and there will be a radius rho right here. So this is this guy. Okay, and if you would like to study the deformation at certain point, because now this is a polar coordinate, like a circular shape. So you need to specify, okay, maybe here is theta equals to 0, and you are focusing on certain position. Here is theta, and here is d theta. Okay, so we are here. That's why the angle right here, this tiny cut of the pie, is having an angle of d theta. Okay, so this is why here is theta. And if you pay attention to this particular point and try to draw a tangent line, okay, you will realize this angle is also theta. So that's why here is theta. But in the drawing, it looks weird. How come theta is the same size as d theta? Because this is an exaggerated drawing. But if you step back and take a look, you realize, oh yes, here is actually theta. Okay? Now, how much deflection we are having? So originally, we have a rectangle, and you can see, you can treat this as y equals to 0. You can say it like that. And after deformation, it kind of deformed in this shape. Right, so it's kind of going up. So right here, the center point on the right kind of goes up. So this is this point. So we treat that increment along y as the deflection. Okay? So how do we get this? This is basically so you need to, here is C, okay? And what is this angle? This angle is basically the angle of the pi. So here is d theta. So there is an arc length right here. This is the arc length. So the arc length is C d theta. Okay. So now all the symbols is being explained in the drawing. Now let's take a look. What is C d theta? C d theta is the increment in length. Originally the length is dx. And this is the length increment. So basically, deformation in x. So if you have deformation over original, this is the original length. What is the definition for that? It's strain. Okay, so that's why C dx over dx is strain. And what is strain? Strain is stress over Young's modulus. And what is the stress for a beam? It's mc over I. So that's why at the end, you have an equation on the left and an equation on the right. And you kind of eliminate C, you end up with this new equation. So d theta over dx equals to m over ei. Okay, it doesn't tell us much, but it'll be used later on. Now, in the second equation, what is rho d theta? So rho is the radius of this rotational radius of this banded beam. So here is rho. And the angle here is d theta. So basically this is the arc length, rho d theta. Okay? Rho d theta. But what's that arc length? That's also dx. So rho d theta equals to dx. And it ends up, you can then derive, actually d theta over dx equals to 1 over rho. So combining the two equations, we will do that later on. We now can focusing on this part. Theta equals to dy over dx. Why is that? Because here, there is a triangular shape. Okay, here is not loading. Here is dx, here is dy, and here is theta. So this is what? Sine. Sine theta equals to dy over dx. But theta is so small, this is close to theta. Not so small, theta is small. So sine theta is close to theta. In this case, you end up with this equation, right? Okay, now you can take derivative with respect to x on both sides. You end up with dx over d theta over dx, and you have y double dot. And what does d theta over dx equals to? Equals to these two. We already derived. So it ends up with these following equation. So the y double dot equals to m over ei. Y double or double prime equals to m over ei. So if we try to compute for y is what? Y is deflection. You can take the integral twice. If you know n, and you take the integral twice, you can get deflection. Okay? So the key is you need to know n. So from this is also another relationship, basically here. Y double prime equals to m over ei. So m equals to ei times double y double prime, right? And we already know if you take a derivative of m with respect to x, you get v. So v equals to this guy, and this is a third order of derivative. And if you do it again, you got w, fourth order of derivative. So now you get all these equations. Okay? So for a beam problem, what's the usual process? We figure out a shear diagram, so maybe just randomly, okay, maybe some shear diagram, okay? So once you have this shear diagram, you figure out the shear force. This is V equals to 0. You know the shear force everywhere. What can you do next? You can take integral of V. Then you got M. So this is a moment. If you take an integral, so this is originally a positive constant. After taking an integral, you should have a positive slope. And this definitely looks like this. This could be something like this. Okay. Just randomly make up something. Okay, so if you do an integral of the shear force, you got moment along the beam. Okay, and if you, once you have the moment, if you would like to compute for the deflection, so how do you get deflection? So deflection equals to EI, and then two more integrals. So if you take two more integrals, you will end up with some kind of shape. This is Y. So probably it looks like this. So the beam is being bended in such a way. Okay? So we are supposed to practice how we achieve these. Okay? We still have a little time. And next week we still have the exercise. Dr. Patel will introduce how some of the problem solving. Any questions? I know you definitely have learned this in the past, but if someone asks you to solve a problem, a big problem, without giving you some notes, I think everyone forget how to do it. Right? So this is a time for you to remind yourself, oh, we have done this. And if I ask you, hey, memorize this equation or memorize this equation, okay, everyone forget. Everyone forget their relationship. So even for myself, sometimes I come back to this subject. I need to, okay, check the notes. Yeah. This is why I learned. Okay? Okay, great. If you have no problems with this, that's perfect. Now we can talk about one problem that I created, which is going to be a more difficult version of your exam, because I promised that I will give you a simpler version for the exam. Keep these. And now, I feel terrible. Okay, this problem. So what is this? There's a bearing on this edge, another bearing on this edge, and there are two pulleys with some belts. And later on, when we learn about pulley and belts, you will know the tension force on both sides of the pulley will be different. That's how the belt can generate a difference of the torque. And the difference of the torque allows this rotational geometry to rotate. This cylindrical object rotates. So that's why you can drive the shaft by a difference of tension forces on both sides of the belt. imagine if you are pulling these two with the same amount of force, it doesn't spin, it doesn't rotate. But the idea is that maybe there's a motor on this edge, the motor is driving the belt, so it's pulling one side of the belt a little bit more, so there will be an imbalance between both sides, so there is a generating some torque, okay? So that torque drives drives the shaft. And because this is driving, maybe there's another belt that is hooked up to a different component, maybe some kind of shaft system that is operating some kind of punching, boom, 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 boom. Yeah. So maybe a motor here driving the shaft, and another belt driving another punching machine, doing some kind of molding, right? So due to the torque generated here from the power of the motor, there will be another torque driving another system. So we know there will be some torque inside the shaft, and there are some weights for every component. So the shaft kind of bends a little. If we design the shaft too thin, it's gonna be weak. So when you put everything on top, it bends too much. If the geometry changed, then it doesn't stay on the same center line, then you can imagine it's gonna vibrate. So if you have real pulley, real bearing, but at the middle it's like chopstick, it's gonna break, right? So, but if you use a super strong metal, it's so heavy, it's so energy inefficient, or maybe because of the inertia, you cannot even drive it. So that's why we need to know how to design it. Now, over here, it gives you numbers of W1, 2, 3, and 4. The first problem is to solve for the reaction forces, okay, on both ends. So I already did the math. Basically, balance of moments. For W3 and 4, so the upper part is the analysis on the XY plane. The lower part are the analysis on the XZ plane, the horizontal plane. So they need to be treated separately. Okay? So let's focus on this XY plane. And because the width right here is 50, total W equals to W3 plus W4 times the width. That will be the total force going up, and it's right in the middle. And I am using, this is also at the middle, so 10 plus 80 plus 50 plus 90 plus half of it, 25 here. So the total force multiplying certain distance, that's generating a counterclockwise moment. That would be balanced out by the reaction force right here. Sorry. So this one, since at the beginning I draw this along positive direction, so it's also generating counterclockwise moment. So RFY times half of it, so the support is right at the middle here. So position 10 plus 90 plus 80, 50, 90, 50, 80, and then 10. So that equals to 0. Similarly, you derive the other three equations. It turns out all the reaction forces are negative. So basically, on the opposite side of the arrows that I have drawn. Okay? So then, I start to draw this shear diagram. So there's easier way to do it on the left. On the right, it's purely by math. Either way is fine. How to do the shear diagram on the left more effectively? Whenever, it's like taking a walk along the beam. Okay, here's the beam, and we are focusing on the y-x coordinate, and we already figured out there's a reaction force going down, 435, and there's another reaction force going down, 965, from the previous slide. And we know there's a portion like this. This will be W3 plus W4. Okay? So drawing a shear diagram is like taking a walk along the beam. You can start from the left. So when you take the walk, when you see any forces along the y direction, that instantaneously change the shear force at that particular point. So this is V along y direction. So right here, you are already being pushed down, so there is a shear of 435. And if you take more walk on the right, there's no more other forces, so this shear force remains until you walk up to here. And when you see distributed loads, the shear force has a relationship with the W. We learned this already. W equals to dV over dx. So if you take the integral of the W, that's shear. So since right here, you have a constant value of the W, so it's like W equals to certain constant value, right? If you take the integral, then you have shear, and you will have that constant times x plus a coefficient c. I can say C1. So no matter what value you have, that's going to be the slope, and you just need to figure out what's C1. And usually the shear force is continuous. So you can plug in the value right here to determine C1. So at the end, it's going up like this. Okay? It's a linear function. And then from here, you continue to take a walk toward right until you reach the right edge, and it's going down 965. If you do this and then it doesn't reach to 0, something was wrong. Okay. So that's I think the easiest way to get a shear diagram. And of course, sometimes you need to do some integrals. So on the right hand side, I already see I give you the integral equation, right? And sometimes you need to plug in to determine for the coefficient. So that's how you get the upper part. And we can, I think the way to get moment, the easiest way is to use the math equation and then take integrals. So, because sometimes you have projective equations. When you have a drawing and you want to figure out how this looks like, our brain is not smart enough, right? But if you have math equations and you take integral, it's easy. So usually for the moment, I will use the equations and then derive for the integrals at each part. But every time you do it, you have a constant coefficient to be determined. So you need to plug into some of the position to figure out what are the values. And since at the beginning you have nothing, so there's no moment. So that would be one position that you can use. And also at the edge. And usually the moment is continuous. So the value on both sides should be the same, something like that. So use some of the boundary conditions, you can determine all the values you need. Then you make the drawing. Okay? So over here you realize how the shear and moment look like. And this is the exact same thing, but along the XZ plane. So I encourage you to practice this. Okay? So next Tuesday, Dr. Patel will bring a problem, and then he will solve it. You will solve it as well. So we have 2 hours to practice in class. Okay, so since we have quadratic functions at different positions, and so there is an extreme value for the largest moment. So by math, I use integral equals to 0, derivative equals to 0 to find out where is the location. So that's the exact position with the largest moment. And for the XZ plane, this is the position. So that means along the XZ plane is being deformed like this. Here the beam is being deformed like this. And along the XY, the hold on. Oh yeah. I draw the, yes. And over here, the beam is being deformed in this way. So it's kind of being twisted in a certain way. But this is only moment, bending moment. Okay? What did I do next? Okay, I also compute for the moment at these 2 positions, because over here there will be a moment along Z, and there will be a certain moment along Y. So it's a moment Z and moment Y. Same here. There is a moment Y and some moment Z. Let's see which one is larger. Okay? So if you view from the right hand side, it's like there's a moment along Z, there's a moment along Y. Okay? So overall, you can compute for M total. M total. So it's actually being like pushed this way, and here is also being pushed some way. Let's see which one is larger. So at the end, I think this one is larger. Yeah. I think I remember this one is larger. I may screw up some of the vector direction. I remember I made some mistake in the previous slide, but you got the point. You basically need to figure out which position has the largest M total. This one at 256 has 106033, larger than the total moment on the position of 134. So this is the critical position. If the beam is going to fail, this is the position. Okay? So what's next? With the information of the largest moment, and we now figure out what's the torque. So torque is easy. You just compute for, because the force on both edge is different. You can compute for torque easily. So we can now study for that critical point and use the stress equation and the shear stress equation, and N being the M total from the previous slide. torque being the value you computed. So you figure out on the surface of the beam, there is a position that is carrying this largest shear sigma and tau. So it will be somewhere, maybe here. I'm not sure if I make the drawing right or not. Here or there, somewhere. So anyway, position-wise, don't worry too much. But if you ignore the geometry of the pulley, just treat the whole thing as a cylinder. At one position, it's carrying the largest normal stress and shearing stress. You can draw a Mohr circle for it. And then you can compute for the principal stresses and the maximum shear stress. Okay, so that's the goal for the entire beam problem. You have components, you figure out where has the maximum shear, you figure out on that particular geometry at which point is carrying the largest normal stress and shear stress, perform Mohr circle analysis, you figure out the principal stresses and the maximum shear stress. And later on, for the design equations, those values will be used. Okay, so I'll see you on Tuesday. Okay, and Dr. Patel will be doing the exercise. Okay, if you have not checked in on the roll call, you can do it.